last lecture, save for some tutorials that you may have with the TA. So this is again on time varying fields and Maxwell's equations. So I have named this one 2. So that it's a continuation of the last lecture that we had. As a review of the last lecture, these are the summary of the Maxwell's equation. So we have the curl or the rotation of E, which is equal to the negative rate of change of the magnetic flux density. So the rotation of E, electric field intensity, will give rise to a time varying magnetic field. And again here, the rotation of H, which is a magnetic field intensity, will give rise to a time varying electric field. And this, the rate of change of D, we have called the electric displacement, which is introduced to correct the inconsistency in the Ampere's equation. And then we have the divergence of D equals rho V, which is the volume charge density, and the divergence of B equals 0, which says that the magnetic field is divergenless because it always closes upon itself. And these are the integral form of the Maxwell's equation. So the first equation is the Faraday's law. The second equation is the Ampere's law. And the third equation is the Gauss law. And the last one means that there's no isolated magnetic charge. Now it's important to remember the integral forms because usually when it comes to the boundary conditions, understanding the boundary conditions and deriving the boundary conditions, we use the integral form of the Maxwell's equation, which is why we are reviewing these equations before we continue. So now we look at the boundary conditions. First, for the electric flux density D. Now, as we see in this diagram, this cylindrical or pillbox shape indicates that we have two medium 1 and medium 2. So we are looking at the electric flux density medium 1 and the electric flux density in medium 2. So for this case of the boundary condition, we resort to this equation of the Maxwell's equation, which is integral d ds equals integral rho v dv. Now, this rho s here is a charge density, which is a surface charge density, and you come to understand why we're talking about the surface charge density instead of a volume charge density. If we are talking about this interface between medium 1 and medium 2, we want to know what happens at the interface. Then we have to assume that the height of this pillbox approaches 0. If the height approaches 0, then this pillbox becomes almost flat, i.e. everything we'll be describing will be at the interface between medium 1 and medium 2. So in the limit as h approaches 0, integral d ds means that the flux density multiplied by the surface area. And for the surface area, we have delta S for the flux density in medium 2, which is dN2, that is normal to the surface. So we have delta S times dN2, and this one, which is below it, minus delta S times d1n, which is in the first medium. Now this must be equal to delta S times rho S. Why delta S? Because in the limit as h approaches 0, this volume now becomes what? A surface. So we can be talking about a surface equivalent to delta S. So delta S times rho S. And we see very easily that delta S is common in this equation. So because it is common, we can actually cancel out delta S, and then we have d2n. that is the normal component of the flux density in medium 2 minus d1n, the normal component of the flux density in medium 1 should be equal to rho s. So what this simply means is that the electric flux density is not continuous across the interface, and the amount of discontinuity is equal to the surface charge density, which is rho s here. Except that in a situation where you have a charge-free interface, that is, there are no charges on the interface, then in that case, rho s will be 0, and then d2n will be equal to d1n. The electric flux density in medium 2 will be the same thing as the normal component of the electric flux density in medium 1, in which case they are continuous. But in general, we can write that in vector form, that the normal component of d2 minus d1 should always be equal to rho s, which is the charge density, the surface charge density at the interface between the two medium. As I said earlier at the beginning, your mics are mute, but if you have a question, you can unmute your mic and then ask your question and then mute it again. Now, if we are talking about the boundary condition, the general boundary condition for the electric field intensity, then we have to look at a box. Which part, or a rectangle, part of the rectangle is in medium 1 and the other part is in medium 2. And the tangential component of the interface in medium 1 is ET1, and that in medium 2 is ET2. We can ignore this M. This M is a fictitious magnetic charge density, which is similar to the electric electric current density here, J. Just so this equation is written in a similar way as to this equation. We discussed this in the previous lecture. So we can ignore the magnetic current density M. Now this rectangle has a height h and the length delta L. Now from the integral form of the Ampere's equation or Ampere's law, we have integral EdL equals the negative integral the rate of change of the magnetic flux density, the surface integral of that. Now, what we say is that, again, since we want to know what happens at the interface, we have to assume that h here is very small, approaching 0, so that whatever we describe will be something that is at the interface. So in the limit as h approaches 0, then this rectangle collapses towards a line at the interface, because this h here is approaching 0, or is 0. And so we have just a line at the interface. If we have a line at the interface, then the surface integral of B will vanish, but the line integral of E will still be present. In other words, since in medium 1, E is along this direction, we keep that to be positive. In medium 2, E is along this direction, that will be negative. So integral EdL in medium 1 will be ET1, the tangential component of the electric field intensity in medium 1, ET1 times delta L. So delta L times ET1, and this in the opposite direction means minus delta L times ET2. Since the surface integral of B vanishes with h approaching 0, then this should be equal to 0. And clearly, since delta L is common to both, we say ET1 equals ET2. So that in summary, we say that the tangential component of the electric field intensity at the interface between the two medium is continuous, because ET1 equals ET2. What about the case of the magnetic field intensity at the interface? Just as we observed in the previous slide, as delta H approaches 0, the surface integral of D here will also vanish. And then, since delta H is approaching 0, then this rectangle, which will have had a surface area, will now be reduced to a line. Therefore, delta S now approaches what? Delta L. So, but the surface integral of D will vanish because there's no longer any surface as delta H approaches 0. And again, since as in the case of E, please mute your mic and only unmute when you ask a question. Again, just as the case of the tangential component of the electric field intensity, the magnetic field intensity also has the same situation. So you have HT1 here and then HT2 here in opposite direction. So that since the surface integral of D vanishes as H approaches 0, then we have for HDL in medium 2, it is delta L times H2T minus delta L times what? H1T. And then delta S now becomes delta L since H approaches 0. So we have delta L times J. Again, delta L is common, and therefore in general, delta L cancels out, and we have H2T minus H1T equals J. And in vector form, we write that the tangential component, this is how you write a tangential component. So N cross H will give you a tangential component, and then N dots, a vector will give you the normal component. Okay? Just as here, N dot this will give you the normal component, but if you do the cross, then you get a tangential component. So H2T will be N cross H2, H1T will be N cross H1, and that should be equal to J, which is the current density. In other words, the tangential component of the magnetic field intensity is not continuous across the interface, and the amount of discontinuity is equal to the current density, J. So that is the general boundary condition, but for different type of interfaces, the boundary conditions will change. So let's consider the case of a dielectric surface. If the surface is dielectric, i.e. medium 1, medium 2, dielectric, then at the interface between two lossless dielectric materials, there are usually no free charges. It means that rho s must be equal to 0 and Js must be equal to 0. Now, in the case of the tangential component of the electric field, we have already demonstrated that it is continuous across the interface. ET1 equals ET2. So that remains the same. And now if we remember that, D actually equals what? Epsilon times E, if you remember that. So then we can say that E1 tangential will be what? D divided by epsilon. So E1 tangential is D1 tangential divided by epsilon 1, and then E2 tangential is D2 tangential divided by epsilon 2. So we can do D1 tangential divided by D2 tangential, and it will be epsilon 1 divided by epsilon 2. So that the interface between two dielectric material, if the dielectric materials are the same, then the tangential component of the electric flux density will be the same. But the dielectric materials are different, then we can't say that they are the same. But the ratio will be equal to the ratio of the dielectric constant, or the permittivity of the two media, epsilon 1 divided by epsilon 2. But the normal component, if you remember, for the normal component, we've already said that D1, D2n minus D1n equals rho s. But in the situation where we are dealing with an interface of dielectric material, there are usually no free charges. So rho S here is equal to 0. When rho S equals 0, then do D2N, the normal component of the electric flux density in medium 2, must be equal to D1N, the normal component of the electric flux density in medium 1. And so you have D1N equals D2N. And as I said, D is epsilon E. So epsilon 1 E1 N, normal component of the electric field intensity, must be equal to the normal component of the electric field intensity in medium 2 times epsilon 2. Again, if the two medium, they are the same, then E1 and E2 will be the same, and this will be the same. But if it's an interface between two medium, then of course the two medium are not the same. They are different medium, and therefore this is the case that stands for the two medium. So D1T divided by D2T, the tangential component of the flux density in electric flux density in medium 1 and 2 will be equal to epsilon 1 divided by epsilon 2. And this is the case for the normal component also. Similarly, as we realize that the magnetic field intensity is also not continuous across the interface, and the amount of discontinuity is equal to the current density J. But at the interface of dielectrics, J is 0. Therefore, H1T must be equal to H2T. And again, remembering the relationship between B and H, what is the relationship? B equals what? Mu H. So since B also equals mu H, then you can say that B1T divided by B2T must be equal to mu1 divided by mu2, as was the case for the tangential component of the electric flux density. And as for the normal component of the magnetic flux density, we have already indicated that they are the same. B2N equals B1N. So that remains the same here. B1N equals B2N. And since, again, B equals mu H, we have mu1 H1N equals mu2 H2N. So if we are required to express the boundary conditions at the interface between two dielectric medium, this will be the case. What is the example of this? An example of this will be, for example, you have a submarine. A submarine is a ship that floats underwater and above water, depending on the requirement. So if the submarine is underwater and it is transmitting signals via its antenna, then the antenna is going to transmit the electromagnetic fields through water, and then it will come into contact with air. So the interface here, an example of that interface is the interface between what? Air and water. So what is the normal, the tangential component of the electric field intensity in water? It will be the same as the electric field intensity in air. But the tangential component of the electric flux density will not be the same as in water and in air. And the ratio of the two must be equal to the ratio of the permittivity in water and permittivity in air. And this is the case with all the other parameters, i.e. electric field intensity, magnetic field intensity, the normal component, and the tangential component. So that is what happens. Therefore, if you are doing a design and you only take into account the field in water, your design will fail, because the field in air, as it is transmitting from water to air, will be different from the field in the water. Now we look at the case of a field at the interface of a perfect conductor. At the interface of the perfect conductor, what will be the example of that? So you're looking at, for example, you're transmitting mobile phone signal, and then you have a case where someone is in an elevator. So the elevator is made of metal. So you have a metal air interface. What happens in the elevator? What will be the condition of the electric field intensity and the electric flux density in the elevator? That is what this boundary conditions seeks to investigate. Now, if you remember, in the interior of the conductor, E equals 0. You remember that? when we did the static electric field intensity, we said static electric field, we said that if you introduce a charge in a conductor, what happens? The charges in the conductor itself begin to drift apart, positive, negative, until such a time that it creates an electric field equal to the original electric field that is causing the drift motion of the charges. And this electric field cancels the other electric field, so that inside the conductor, the electric field is zero. So the electric field intensity inside the interior of the conductor is zero. If E is zero, you remember from the Ampere's circular law of the Maxwell's equation, integral E dl equals the negative integral del B del T times ds. So if E equals zero, then it means B here will also be equal to zero. So that in the interior of the conductor, B also equals zero. And then D again equals epsilon E, but E equals zero. Therefore, D again must also be equal to zero. Then H, which is equal to B divided by mu, which is the permeability of the medium, must also be equal to zero, because B here is also equal to zero. Which means that in medium 2, E2 equals 0, B2 equals 0, H2 equals 0, D2 equals 0. Everything in medium 2 equals 0. So which explains why in some elevators, depending on the material that is made, if the material approaches a perfect conductor, you see that you enter into the elevator with your phone, and then suddenly your signal, mobile phone signal, goes to 0. You can't receive a call. So the material of an elevator must be made such that its conductivity is relatively lower than that of what? A perfect conductor. If it is a perfect conductor, all the field inside the conductor will go to 0. And then in the interior of the conductor, the field is equal to 0. And chances are that if you are in the elevator, you may not receive any signal. So the field at the interface of a perfect conductor is that, you remember in the general case, the tangential component in medium 1 must be equal to the tangential component in medium 2. But the tangential component in medium 2 is 0. So then that one in medium 1 must also be equal to 0. But for H, the normal component of H the difference equals J. Therefore, if that in medium 2 is 0, then N cross H1 must be equal to what? JS in medium 1. And then the difference again for the normal component of the electric flux density, D1N minus D2N should be equal to rho S. If D2N equals 0, then D1N must be equal to rho S, which is the surface charge density. And then finally, since B1N must be equal to B2N, as we saw earlier here, B2N equals B1N, then if in medium 2, B2N is 0, then B1N must also be equal to 0. So these are the boundary conditions at the interface of a perfect conductor. Not just any conductor, a perfect conductor. Only the normal components of the electric field intensity and the normal component, the tangential component of the electric field intensity and the normal component of the electric flux density will be present, not the tangential component of the electric field intensity or the normal component of the magnetic field intensity. So that is about boundary conditions. If there are questions on the boundary conditions, we can ask, and then we continue to the next phase of the presentation. If you want to ask a question, you'll have to unmute your mic, and then I can listen to your question and answer. Okay, so if there are no questions, we go to the time harmonic electromagnetic fields. As we mentioned earlier in the discussion, electromagnetic field is such that you have the electric field and the magnetic field, and the electric and magnetic field, they are coupled together, as we saw in the Maxwell's equation. the electric and the magnetic field, they are coupled together. So if you look at here, you have the electric field intensity, the magnetic field intensity, and they are coupled together in an equation, because the change or the rotation of the electric field gives rise to the magnetic field. Here, the rotation of the magnetic field gives rise to an electric field. So the two fields, they are coupled together. And we said also that they vary in space. So if you look at the Cartesian or the rectangular coordinates, E will vary along X, Y, and Z. B will also vary along X, Y, and Z. But as you see here, they do not only vary in space, they also vary in time, because B varies with respect to time here. In other words, the field quantities vary with both space and time. And therefore, if you look at the electric field intensity, typically, it must be a function of X, Y, Z, and T in the rectangular coordinate, where T is a variable of time. Now, the variation of the time, or the variation with respect to time, can be represented by a sinusoidal quantity, e to the j omega t. And therefore, if we are looking at sinusoids, then we are looking at functions that are cos omega t. Functions that are cos omega t. Now, cos omega t this cos omega t here is the real part of what? E to the j omega t. Because e to the j omega t must be equal to what? Cos omega t plus what? J sine omega t. But we are only interested in fields that are what? Cos omega t, sinusoidal quantities of cos omega t. And therefore, we have to take the real part of this equation, because ej to the omega t will give us both cos omega t and j sine omega t. Now, if we take the real part of this, then we are only dealing with what? Cos omega t. So this equation is E cos omega t, E varying along X, Y, and Z, and then this, the real part of this will give us a cos omega t. So that E will just simply be what? In simple form, it will be what? E cos omega t. So that will be E. This one here represents E cos omega t, except that the E varies with what? X, Y, and Z. So E is function of both space coordinates and time. Similarly, the magnetic field intensity also varies along X, Y, Z, and T. And the T component, or the T variation, is represented by Ej to the omega t. But again, we have to take the real part, because we're interested in what? Cos omega t. So that this becomes H cos omega t. So represented like this, then we are looking at time harmonic, because it's a variable, or it's a variable of time that we're dealing with here. And for time harmonic electromagnetics, if E equals Ej omega t, E to the Ej omega t, if you differentiate it, delta E, delta t, you have what? J omega times E. Why is that the case? Because if you differentiate E to the J omega t with respect to t, then this will be equal to what? J omega again times what? Ej omega t. So if this was Ej omega t, then we'll still have E here. But this quantity here, e j omega t, was the initial e. So this then becomes j omega times e, because the initial e was what? E j omega t. Therefore, if you differentiate it, if you differentiate e with respect to t, you get j omega e. If you integrate, you get e divided by j omega. If you differentiate h also, you get what? J omega h. And if you integrate, you get h divided by j omega. So if we take this into consideration, if you look at the Maxwell's equation, we have curl of E equals negative del B del T. If we write B as a function of time with EJ omega T, then del B del T will be what? J omega B. If you understand what I'm saying. So this will be J omega B. But again, B equals what? Mu H. And therefore, for the first equation, curl of E will be minus J omega mu H. This mu H is B. So J omega B minus J omega B is actually this minus del B del T is equal to minus J omega B. But B again is what? Mu H. So B is replaced by mu H here, and you have curl of E equals minus J omega mu H. Similarly, curl of H, which was what? The curl of H was equal to what? J plus del D del T. But we are dealing with source-free field. If the field is source-free, then it means J here equals what? Will be equal to 0. If J equals 0, then curl of H must be equal to del D del T. But del D del T must be equal to what? J omega D, since we are dealing with sinusoid. And this D here again is what? Epsilon E. So J omega epsilon E will be the curl of H. And therefore, time harmonic expression for the Maxwell's equation in source-free, linear, isotropic, homogeneous, and lossless region. Linear means that the field varies linearly. If you multiply by a constant, it will just be, the field will just be multiplied by a constant. You don't have H varying as a square or cube or whatever. Okay, and it is also homogeneous because it's in the same medium, therefore it is isotropic. And it is lossless. We are not considering losses in this case. So curl of E here equals J omega H, J omega mu H, and then curl of H, J omega epsilon E. This is a time harmonic expression of the Maxwell curl equations, only for the curl equations. Now we can take a second curl for this first equation. If we take a second curl for this first equation, to be curl of E equals minus J omega mu, then curl of H. But this curl of H here, we already have that here. Curl of H equals J omega epsilon E. So instead of curl of H here, we substitute with what? J omega epsilon E. And when we do that, this curl of H here becomes J omega epsilon E, and we have minus J omega mu. Minus J times J is minus 1, and that cancels this minus. Omega times omega is omega squared, and then you have mu, you have epsilon, and then you have E. So that the curl of E will be equal to omega squared mu epsilon E. Now, there is an identity that allows us to express this part of the equation in this form. This is the divergence of E, the gradient of the divergence of E minus gradient square of E is equal to the curl of the curl of E. So it means that instead of curl of E, we can use this part of the equation, which is the gradient of the divergence of E minus gradient squared of E equals mu omega squared mu epsilon E. And now we can further simplify this part of the equation. How do we simplify that? Since it is source free, then rho s equals 0. But from divergence of D equals rho s, it means D equals 0. D also must equal to 0, since rho s is 0. And then divergence of E also equals what? Rho s divided by epsilon. Therefore, divergence of E will be 0, and E itself will also be, this divergence of E will also be equal to what? 0. And therefore, the identity that we said, the gradient of the divergence of E, this divergence of E here is 0. So the whole part of this equation here becomes 0. If this is 0, then we are left with minus gradient squared of E. That is this one. So it means the whole of this equation can be replaced by minus gradient squared of E. And therefore, minus gradient squared of E equals omega squared mu epsilon E. Or we can write this as gradient squared of E, that is if you take this one here, plus omega squared mu epsilon E equals 0. This equation here is called the wave equation. And it is the basis for all wave propagation, which has resulted in all of the wireless communication that we have here. So it's a very, very important equation. And from this, we can see how it was discovered that a wave, an electromagnetic wave, can propagate with the speed of light. And if the electromagnetic wave can propagate with the speed of light, then it is possible for us to impress a message signal on the electromagnetic wave and allow it to propagate with the message signal such that we can establish communication at a distance. And that is what you did in analog communication when you had a carrier wave, which is your electromagnetic wave, and then you impress on the carrier wave a message signal, voice signal, for example, which is your modulating signal. And that will modulate the carrier wave and then propagate to a very far distance. And so we have wireless communication that allows us to do AM amplitude modulation transmission. So we have AM radio, we have FM radio, we have mobile communication, we have Bluetooth. All of that is as a result of this equation here, as we shall see pretty soon. So this equation is called the wave equation. Similarly, you can write the wave equation for the magnetic field intensity, the del squared H, or the gradient squared of H, plus omega squared mu epsilon H also equals 0. Now, this quantity here, omega squared mu E, mu epsilon, we can replace with a constant, because it's all constant. Omega is 2 pi f. If you're given the frequency, the omega is constant. Mu is constant and epsilon is constant. So you can represent that by k squared equals omega squared mu epsilon. That means that k must be equal to what? Omega square root of mu epsilon. If you look at the slide I uploaded to the site, this is actually squared. So that is wrong. You have to correct it to this one. So k equals omega square root of what? Mu epsilon. This k is called the wave number. Another name for k is what? Propagation constant. Actually, strictly speaking, it is what? Phase constant, because the propagation constant must take care of attenuation, which is the losses. But remember, we started with the case of what? A lossless region. So since it is a lossless region, the losses will not be introduced, and therefore k here can simply be called the propagation constant. Full k propagation constant will include losses, which will include the attenuation, but that is not included here. So another name for the wave equation, if we put k in place of omega squared mu epsilon, so we have k squared here. Another name is called the Helmholtz equation. So we can either call it the propagation equation, the wave equation, or the Helmholtz equation. And so the two Helmholtz equations are del squared E plus K squared times E equals 0, and then del squared H plus K squared H equals 0. Now, if you remember the expression that represents del, and therefore del squared, then you know that this is what? A differential equation. So what is the expression for del? Del is given by del equals what? Del x. So this is ax plus ay, that is in rectangular coordinates. Del y plus az del z. But if you do del squared here, then the ax will vanish, right? And then this ones become squared. This one is squared, 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 squared. So that is the del squared. Sorry. That's del squared here. So now if we assume that E only has x components, because E itself must be written as what? If you remember, E is a function of what? X, Y, Z, and T. But the T aspect is taken by what? E_j omega T. So X, Y, Z, which means that this must be the same thing as what? EX plus AY EY plus AZ EZ. As you can see, it's very difficult to write with the mouse. Maybe one of you should get me a pen mouse, so it is very easy to write. So if E only has X components, then only AX, EX is present. And then the others are not present. And this is only for simplicity. And again, if it varies uniformly in the X, Y plane, uniform variation means there's no change in Y, no change in Z. So it means this is also not there. So we are simply left with del squared, del x squared, and only what? EX. So then this becomes del squared EX del Z squared. Sorry, the variation is uniform along XY. So only Z's variation is present. This should actually be Z. Sorry. Del Z squared. Oh, sorry, del squared Z, I should say. Del squared Z. Del Z squared, okay. So del Z squared is present and EX is present. So you have del Z squared EX plus K squared EX, and this should be equal to 0. And as you can see, this is what? A second order differential equation, ODE. And I believe you have been taught how to solve ODEs. And since this is not a math class, I'll simply state that the solution for an ODE of this nature is EX, because only the X component is present, varying along the Z axis, is a certain constant E plus E minus JKZ plus another constant E minus E plus JKZ. These are constants and whose values can be determined or they serve as the amplitude of the wave that is being propagated. We've already have seen what K is. K is the wave number, and the Z here is the distance traveled. So if we are to express this in time domain, remember I said that in time domain, we take only the real component of the wave. If you take the real component of EJ omega t, then we have E plus, there's J omega t here, and there's what? KZ here, so minus KZ. This minus JKZ, if you multiply with E minus JKZ, if you multiply by J omega times AE J omega t, this will be equal to what? You just add the exponent. So this will be E J into brackets omega t minus what? KZ. So E to the J omega t minus KZ. If you take the real part of this, RE will be what? Simply cos omega t minus KZ. And so that is what is represented here. So you have E plus cos omega t minus KZ plus E minus cos omega t plus KZ. Now this component of the wave, which is EX traveling along the traveling along the Z direction, E traveling along the Z direction, this is actually a wave traveling forward in the positive Z direction. How would you know that? For this wave to reach zero, then it must have been traveling from this direction until it reaches zero. Because this is minus KZ, so it must be traveling from backwards here until it reaches zero. So that's a positive traveling wave. But for this one to reach zero, since it is plus KZ, it must be going backward this way to reach zero. And therefore, this one is the forward traveling wave, or the plus Z traveling, and this one is the negative traveling wave. This kind of equation of the forward and the backward traveling wave is something, again, that you would meet in your future studies, especially in microwave, because these waves are always together. The EX, or the field, is always made up of two components, of a forward traveling wave and a backward traveling wave. So you can look at this as a reflected wave. Unless there's no reflection, there's always the forward traveling and the backward traveling. So this is a sinusoidal wave at different time scale. At t equals 0 is this one here. And at another time, t equals t1 is this one here, the blue one. And at another time, t equals t2 is the green one. And t equals t3 is the black one. So continuously, the wave keeps traveling along the Z direction. Now, this here is the, if you want, the most important aspect of this demonstration, because you look at omega t minus kz here, which is supposed to be a constant because the variation has to be constant, then omega t minus kz must be equal to a certain constant, right? Or we can write that z here, if you make z the subject, should be equal to constant plus omega t divided by k. So z equals, sorry, z, if you want k here, we have to take kz to the other side, and this will be omega t minus constant, and divide by k, we get z. So z is omega t minus constant divided by k. And now, since z is a distance, we can differentiate z with respect to t. If we differentiate z, which is a distance with respect to t, we get a velocity. This velocity is called Vp, or the phase velocity. So the phase velocity is the z dt. And what is z? Z is what? Omega t minus constant divided by k. So omega t minus constant over k. If you differentiate this one with respect to t, this will be omega if you differentiate with respect to t. So this is omega, but constant, if you differentiate with respect to t, it has to go to 0. And then this is divided by k. So you have omega divided by k. Now, omega divided by k. What, if you remember, what is the expression of k? K was given as what? Omega times square root of what? Mu epsilon. Therefore, omega divided by k means this will be what? Omega divided by omega square roots of mu epsilon. So omega cancels out and you have what? 1 divided by mu epsilon. And that is Vp, called the phase velocity. Now in free space, this mu here will be equal to mu naught. Epsilon will be equal to epsilon naught. And you remember their values. What is mu naught? What is the value of mu naught? Mu naught was equal to 4 pi times 10 to the power minus 7 henries per meter. And epsilon naught was equal to 8.85 times 10 to the power what? 12 times 10 to the power 12. So if you put this in here, this Vp here will evaluate to almost 3.0 times 10 to the power 8, which is the same thing as what? C, the speed of light. So by this, we're able to tell that an electromagnetic wave is able to propagate and travel with the speed of light, which is 3 times 10 to the power 8. And this is how come it was discovered that it is possible for message signal to be impressed upon an electromagnetic wave, which will travel with the speed of light and therefore take that message to a distance lag. And therefore wireless communication was born. And this was actually practically experimented and demonstrated by a scientist called Marconi, who did the first transmission, wireless transmission between 2 points. So you can see that all wireless communication actually depends on electromagnetic wave theory. And from this, we see that any such wave must travel at the speed of light. Is that a question? Is that a question?
No. Is that a question you don't go answer?
Okay. So any such wave must travel with the speed of light given by Vp here, which is 3.0 times 10 to the power 8.
They can understand the class. Then they hear me.
Please, if you're talking, you should be asking a question. Otherwise, you should mute. Okay. Now, again, what is a wavelength? The definition of a wavelength. Wavelength is a distance between what? Either 2 crests or 2 throws, right? Or the distance between same points. So if you start from here 0, from this distance to this distance, where it starts again from 0 is a wavelength. And this distance usually is a distance of what?
Sir, please come again with the wavelength description.
Wavelength is a distance between the same points on the wave, two successive points on the wave. So 0 here, you can start from 0 here, the next 0 point, that distance is a wavelength. Or you can start from a crest here, and the next crest here, you have a wavelength. Okay, so two successive points on the wave.
Okay, it's fine.
So that distance there is 2 pi. If that distance is 2 pi, then it means that omega t minus kz here, after a wavelength, must be equal to 2 pi. So if you come here, omega t minus kz minus omega t minus kz plus lambda, that's after a wavelength. This should be equal to 2 pi. The difference between these 2 points should be 2 pi. Obviously, omega t here will subtract omega t here, so 0. And then kz here minus kz minus negative kz. Kz will also be 0. So you have what? Minus times minus k lambda. So that's k lambda, which means effectively k lambda equals 2 pi. And then we can say lambda equals 2 pi divided by what? K. If lambda equals 2 pi divided by k, you know what the expression of k is? This is the same thing as 2 pi divided by omega square root of what? Mu epsilon. But what is omega? Omega itself is 2 pi f, isn't it? So we have 2 pi divided by 2 pi f times square root of what? Mu epsilon. So here you can see that 2 pi cancels out, and we have 1 divided by f times square root of mu epsilon. Now in free space, what is 1 over mu epsilon? 1 over square root of mu epsilon is what? In free space, we said it's the speed of light, isn't it? 1 over mu naught epsilon naught is c, which is the speed of light, or the phase velocity. So this is actually v. 1 over mu epsilon is v, and therefore we can write that this is the same thing as vp divided by f equals what? Lambda. And then your famous expression vp equal f lambda can be verified, where vp is the velocity of the wave that is being propagated, equals the frequency times the wavelength. So, or lambda equals vp over f here as verified. Now we can find h also in terms of what? E, because curl of E equals minus j omega mu h. Therefore, if you perform this operation, curl of E, and I know you have done that in your tutorial sessions. So E is only EX. Curl of E actually will be curl of E is equal to what? The determinant AX, AY, AZ, then del X, del Y, obviously, and then del Z. And then you have EX, EY, and then EZ. Okay, but remember that we said that we are considering E, which is only a component of EX. So we don't have EY, we don't have EZ. And we said that the variation in the X and Y are also uniform. So the X, the DDX and DDY are also 0. Therefore, what we have here is what? This is 0 here, and this is 0 here. This is 0 here, and this is 0 here. So if you perform this curl operation, obviously, the only component that will be there will be the Y, the AY component. And the AY component will be given by what? Negative del EX. Sorry? Is that a question? Okay.
Fed them.
Please, you speak only when you are asking a question. Can you hear me? Speak only when you're asking a question. Yeah. This people, they are the same online or in normal class. They're always the same. Please, quiet. So this minus del EX del Z, if you differentiate this one, this EX, if you differentiate this with respect to Z, you assume that we are starting from t equals 0. If t equals 0, then this is E cos kz, isn't it? Because there's no omega t equals 0. Or let's write it in the form of the EX of Z will be equal to E plus then E to the power minus J kz plus E minus E J K Z. So that is this equation here that we are using. So if you differentiate this one with respect to Z, then you have minus JK so this will be what? Minus JK into brackets. This will be JK, okay? But I'm taking the JK out. So this will be E plus EJKZ. That's minus. So since I'm taking minus JK out, this will be minus also. E minus EJKZ. Okay, so that's now from here, curl of E equals minus J omega mu H. We can see that H equals what? 1 over minus J omega mu curl of E. Now this curl of E the curl of E is this. This is curl of E. Is equal to this. So it means that we need 1 over minus J omega mu times curl of E to get H. And if you divide this by minus J omega mu, this will also be divided by minus J omega mu. So minus J cancels out and you simply have what? K divided by omega mu times the whole of this. But we have an expression for K, don't we? K is omega times square root of mu epsilon divided by omega mu. So omega cancels out, and then this will simply be equal to what? Square root of epsilon divided by what? Mu. Now this factor is called 1 divided by eta, where eta is the impedance of the medium. In this case, impedance of free space will be equal to this. And therefore, if you want eta, then eta must be equal to square root of what? Mu over epsilon, the inverse. And if you take mu for free space, it's mu naught, and epsilon naught. If you put in these values, you get 377 ohms. So it means that the impedance of free space is 377 ohms. And the speed of light, or the speed of wave propagation, 3 times 10 to the power 8. So these are some of the constants that you encounter throughout your study as far as wave propagation is concerned. So this is how the wave is propagated. So you see that only what HY is present, and then we also have EX. So it's EX and HY that are present. So this is your E, which is along the x-axis, varying sinusoidally like that. Sorry. E along the x-axis varying sinusoidally, and then Y along the y-axis also varying sinusoidally. So the Y is in blue and the E is in red. If you look at it on the XY coordinate in plane, so you have E along the x-axis in red, and then the the H along the y-axis in blue, plane by plane. So this way we see that the E and the H are traveling along the z-axis, but the E is perpendicular to the y-axis, to the H. So the electric field being perpendicular to the magnetic field is what we call the transverse electromagnetic wave. Transverse electromagnetic wave means the electric field is perpendicular to the magnetic field, and both are traveling along the z-axis, as you see in this. So this is the end.